All right, section 4.3 is going to build on what we did in 4.2. In 4.2, we learned about prime factorization, and we've learned about factorization as well, but in particular, we learned about prime factorization. So what we're going to work with in this section is a way of comparing or incorporating that at least within two numbers or more. And so we're going to do that with greatest common divisors and least common multiples. I'm going to start with the greatest common divisor one. A greatest common divisor, or sometimes called a greatest common factor, and you've seen them abbreviated GCDs and GCFs. It's what you use when you get to fractions to find a denominator, a greatest common denominator, or a least common denominator. You're using those ideas. So that's sort of the overlapping piece for the least common multiple. What this is, a greatest common divisor, is it's a greatest whole number that divides all of the numbers in your set. The one thing I want you to be aware of is that the word greatest, this is the extent of my, my grammar lesson for the day. The word greatest is an adjective that modifies the word divisor. That sounded Englishy, didn't it? Oh, yes. Greatest does not mean it's a big number, okay? In fact, it will be a number smaller, usually smaller, than the numbers you're working with. It certainly can't be a number any larger than the numbers you're working with because it has to be a divisor. So if you think about the numbers we've been working with, like the number 100, we used that one just a minute ago, Carly, right? The number 100 has lots of divisors, but the divisors of the number 100 need to be numbers that divide it. So like 2 and 4 are divisors, but they're small numbers, right? Okay, so the numbers we're working with when we're working with greatest common divisors are numbers smaller than the number itself. Write that down, please. It's really common to get the ideas between greatest common divisor and least common multiple mixed up in your mind because you think of the word greatest meaning something that's large, and it's not. It's a divisor, which means it's something small. So it's the largest of a bunch of small things. And we've come across this idea before. The word relative, or the phrase relatively prime, are two numbers or multiple numbers whose greatest common divisor is 1. So remember when we talked about the number 24 last time, and we said if we wanted to know if something was divisible by 24, it was perfectly fine to use the numbers 3 and 8 to make that decision, but not okay to use the numbers 4 and 6, because 3 and 8 were relatively prime. They have no factors in common. But 4 and 6 are not relatively prime. They have the number 2 as a factor in common. Okay, so the relatively prime is the idea that we encountered before. So there's several ways that we can find greatest common divisors for sets of numbers. We're going to do a set of two numbers, 12 and 15, and we're going to do it using the intersection of sets method. All right, so to do the intersection of sets, what you do is you list all of the divisors of each value, and then you look for the one that's the biggest number in both lists. So we're going to start with the number 12. The first and smallest divisor of any number is the number 1. It will be always in the list. What's the next number that divides 12? 2. And then what? 3. And then 4. 6. And finally 12. So no number in this list is bigger than 12, right? Right. Okay, we're going to do the same thing with 15. What numbers do you have? 1. Good. And then we look at these lists and we say the biggest number they have in common is 3. So the GCD is 3. It is the greatest divisor. This is intersection of sets. This works pretty well if the numbers are small, or if they don't have a lot of divisors, right? But if we had done a larger number or a number that had lots and lots of divisors, this would be kind of tedious. Prime factorization method is another method. Now this sort of beckons us back into section 4.2 where we were finding prime factorization for numbers. So you'll see that I chose purposely numbers that are a little bit larger for us to work with because that's the kind of numbers you would see used for this method. 400 and 360. All right, so what we're going to do is we need to list out the prime factors. We need the prime factorization. So I'm going to do the number 400 as a division tree or a division list. I don't know. We need a name for this. Somebody needs to come up with a name for this for me. That should be your homework over Easter. What's a name for this method? Division brick? That's pretty good. I like that block brick. I like brick. That's good. All right, so smallest number that divides 400. That's prime. 2, yeah. So we don't want to start with 1 is what I'm just getting at. Okay, so then that gives me 200. Then what? 2 again to give me 100. And then 2 again to give me 50. And then 2 to give me 25. And finally, we get 5 and 5. Okay, so let's do 360. Smallest number? 2 to give me 180. And then to give me 90. And then 2 to give me 45. Resist the urge. What's the next one? It's actually 3. I know you guys all wanted to do 5 next. 3 is actually the next one, which would give me 15. And then 3, which would give me 5. Okay? So here's what we do with the prime factorization method. So we've done the construct the prime factorization of each number. We're going to choose all the prime factors that are common to each factorization. Okay, so actually let's write these out first. It doesn't actually say that, but let's write them out here. So 400 is 2 to the what? So 4. Yeah, and then 5 to the 2. And then 360 is 2 to the what? 2 to the 3, and then 3 squared and 5. Okay, so it says choose all prime factors common to each factorization. So what prime factors, that is the bases of these, do they have in common? They both have a 2 and a 5. Now, we're not done, because the step 3 says to list the prime factor with the smallest exponent. So what is the smallest exponent on any of the 2's in the prime factorization? 3. There are at least 3 of them in each of these numbers, right? And what about 5's? There's 1 of them. And then we would write our answer as finding out what that value is. 2 to the 3rd is 8 times 5 is 40. So the GCD is 40. The other thing that you can do, although it doesn't fit in with my nice neat little list up on top, is that you can look at these factor bricks. Bricks, I like it. We can look at these bricks and we can go across and we can compare them as well and say, look, there's a 2 here. That's 1 2 in common. There's another 2 in common. There are 3 2's that are in common. And then there is 1 5 that's in common. And then everything that was not circled would not be included. So we only circled the common ones. So there's 3 2's, that's 2 cubed. There's 1 5, that's 5 to the 1. Okay, look good? This is probably the one that you remember doing the most. This seems to be the one that I remember doing the most anyway. Here's another one. This is division by primes. This is an interesting method. It looks very similar to the last one, but instead of doing it in 2 separate bricks, we're going to do it all at the same time. So here's how this works. We write the 410 here and the 360 sort of next to it, and we draw our division bar sort of underneath, or brick underneath. And instead of looking for any number that divides them, we want to look for prime numbers only. Okay, that's the same. But it has to divide both of them. So what's the smallest prime number that divides both of them? 2. So 410 divided by 2 is 205. Yeah, the numbers did change, beware. And then 360 divided by 2 is 180. That one actually is the same number we had last time. And we do it again. But we notice when we do it again that they are not both divisible by 2 any longer. One of them still is, but that's not good enough. We need both of them to be. So the next prime number would be the number 3. Do they both divide by 3? No. 205 does not divide by 3. How come? It adds to 7, right? So our next prime factor would be the number 5. And do they both divide by 5? Yes. All right, so what is 205 divided by 5? Good. And what is 180 divided by 5? 30 what? 36. Okay. Now we look at 41 and 36. And we ask ourselves, are there any prime numbers left that divide both of these? The answer is actually no, and it's pretty quick to answer no because 41's prime. If there were, we'd just do this again. We'd do the same bar underneath again, and we'd keep going. If we're not, I mean, if we've got numbers at the end that are relatively prime, which these now are, then we stop, and these two numbers here on the sides, 2 times 5, is the greatest common divisor. So it's 10. I kind of like this one. It has some limitations. Like, you don't actually see all the prime factors written out for each one of them, so if you had a question that asked you to do that as well, you wouldn't have that piece done. But it definitely is nice that it sort of does both things at the same time. It's kind of a neat feature. All right, one more. I think there's one more. Next one is called the Euclidean algorithm. This one is the least like the others. Okay, this one's the most different. The way that you do this one is you divide the larger number by the smaller one, and you get a remainder. And you use that remainder to continue this division process. So let me show you. Okay, so we use the larger number divided by the smaller. All right, and I really don't care how many times it goes in. Your calculator can find this for you. But how many times will 72 go into 126? Just once. This one's not too ugly, but, and then I need 126 minus 72. What's that one? 54, right. The reason I said I don't really care how many times it goes in is because this algorithm is dependent completely upon the remainder. I really care about the remainder in these problems. Okay? I take the remainder and I take the divisor and I do the problem again. Now the remainder has to be smaller than the divisor, but you should have done that, or I mean that already automatically happened if you did the division right. So the remainder goes on the outside. The number you originally divided by moves under now, and you do it again. How many times does 54 go into 72? Once. I promise they don't always just go in once, but this one did. So then we subtract that. So what is 72 minus 54? 18. So I use the remainder and the original, not the original, but the divisor, the one I just used. So the divisor goes on, I'm sorry, the remainder goes on the outside, divisor goes underneath. How many times will 18 go into 54? It is 3. What is 3 times 18? It's actually 54. At the point when I get a remainder, the GCD was the last number I divided by. Isn't this a strange method? It's very different than the other ones, isn't it? Really is. All right, but the answer is just simply the last number divided by. Notice the divisor, the numbers here up on top, 1 and 3, have absolutely nothing to do with the answer to the problem. So don't get yourself confused. It's all about the remainder and the divisor. All right. The next part of our lesson is about least common multiples. So I think we're going to stop here because it'll be more cohesive to do all that together and stop with greatest common divisor.